Hello students, welcome to lecture 24 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today we will be going into more details of single and double negative metamaterials. So here is the lecture outline. We will give a brief introduction to this single and double negative metamaterials. We will also discuss about the wave propagation in single negative or double negative media, that is SNG and DNG media. We will also go into a bit of details of double positive medium, that is DPS, single negative SNG medium, and double negative, there is a typo, this should be DNG, okay, DNG medium. And we will also look for the in-depth analysis of left hand metamaterials and discuss about negative refraction and some of its applications. So in the previous lectures we have discussed about metamaterials. We understood that metamaterials are basically those materials which have engineered unit cells, and these unit cells basically give you some control on the properties which are otherwise only found in natural materials, or you can completely come up with exotic materials which are not found in nature. Something like you can design materials with own customizable plasma frequency. You can also look for negative permittivity, negative permeability materials and so on. And why we are bothered about permittivity and permeability? The reason is the propagation of any electromagnetic wave through a linear isotropic medium is governed by these two parameters, which are the electric permittivity epsilon and the magnetic permeability mu of that material. So in general these quantities are frequency dependent and they are complex, okay, and the wave properties such as propagation constant, velocity, attenuation constant, impedance, dispersion relation, all these different properties can be easily obtained from epsilon and mu. And the signs of the real and imaginary part of this epsilon and mu at a particular given frequency govern the various regions of propagation. So as we mentioned that permittivity can be frequency dependent, mostly they are frequency dependent in almost every material, and they are also complex values. So there is a real part, there is the imaginary part. So depending on those real and imaginary components, you can find out that how the wave propagation takes place. Now if you consider a media which has got a permeability mu which is real and positive, that means that particular medium does not support magnetic absorption or amplification, okay. So in that case the wave propagation characteristics mainly depend on the signs of the real and imaginary parts of the permittivity epsilon, okay. So in those materials epsilon plays the most important role. Now if you remember, initially we have discussed that at optical frequencies most natural materials known to be non-magnetic. So their mu you can simply take as mu r, okay, or you can say mu r is basically 1. So mu is same as mu naught, okay, they do not have any magnetic properties. So in that case the real and imaginary part of the permittivity epsilon that depend or that dictates the wave propagation characteristics. Now similarly, if you think of the other extreme, that where your permittivity is real and positive and you have a fixed value there, okay, in that case the magnetic properties which is described by mu, okay, that will dictate the nature of wave propagation. And magnetic media such as the media which includes some metal components that could carry induced electric currents and generate magnetic fields, they generally have a complex value of mu with real and imaginary part which may be either positive or negative, right. So in most general case the manner in which the signs of the real and imaginary components of permittivity epsilon and permeability mu they come up, okay, they will dictate the characteristics of wave propagation, but usually the contribution is not that prominent, it's subtle. Okay, we'll look into some of these examples in this particular slide. So if you remember this epsilon mu diagram, that actually classifies all different natural materials and metamaterials, or everything can be classified from this epsilon mu diagram. Okay, so if we confine ourselves mainly to lossless and passive media in which there is neither absorption nor gain, we can say that we are basically operating away from dielectric and magnetic resonances. Okay, and under these conditions you can say that epsilon and mu are real and their signs may be positive or negative. And when you think of those cases, so when you have permittivity to be, the permittivity and permeability, if you consider them as real quantities, you can have these four possible variations. The first one, or the first quadrant, as you can see here, basically denote epsilon greater than 0 and mu greater than 0. That means you are talking about double positive materials where both mu and epsilon are positive. So in this case, this kind of materials are basically transparent, and they have positive refractive index, and ordinary dielectric medium, whatever you see, all the common dielectrics, they all fall under this particular category, okay, of double positive materials. Then the next category belongs to single negative materials, where either epsilon or mu is negative. So in this particular case, the second quadrant, okay, here epsilon is negative, mu is positive. Okay, so this is basically, it's a negative permittivity materials, this one, but we can call this also as a single negative metamaterials. This one also single negative metamaterials, but here mu is basically negative. And single negative metamaterials are basically opaque, but they could support optical surface waves at the boundaries with double positive materials. So these are the simple example you can take as the metals at optical frequency. They are basically this single negative metamaterials, okay, or you can say single negative materials, and they support surface waves which are also known as surface plasmon polaritons to propagate along the metal dielectric interface, right. So here are the examples. So metals such as gold, silver, they exhibit negative permittivity while maintaining positive permeability in the infrared and visible spectral region. So when we talk about electrical plasma, those are basically, we are talking about metals at optical frequency, and one thing is that wave propagation is not permitted. They basically support evanescent waves inside them. However, remember that on the surface, you can actually, on the surface with a double positive material, you can actually have some sort of surface waves which are basically the surface plasmon polaritons. Now if you look into this particular third quadrant, the third quadrant, you see both permittivity and permeability are negative. So these are called as double negative metamaterials, and they are also called as left-handed media. We will see that in subsequent slides. So all other quadrants, the media is basically a right-handed media, but in this particular quadrant, the third quadrant, okay, here you can actually see that the E cross H, they follow left hand thumb rule. Okay, so they also give rise to something which is completely unnatural, that is like negative refractive index, and you can if you apply Snell's law of refraction on a boundary between this kind of double negative and double positive kind of material, you will see a negative angle of refraction. and that is something completely shook the world with surprise, that this is something completely out of the world you can think of, and you can also realize this using the techniques that have been developed. So you see, this kind of material also support wave propagation, but the direction of wave propagation and the direction of the Poynting vector here are opposite, they are not in the same direction. Okay, as you can see here, the in this case the k vector, that is the wave propagation, happens in the backward direction, whereas the energy propagates in the forward direction. But if you look here, in the case of double positive, E cross H, if you are using the right hand thumb rule, you are seeing that the wave propagation happens in the forward direction, that is the right direction. Also energy propagates along the right direction. S is basically the Poynting vector. So we will look into that very soon, okay, how the Poynting vector is calculated and why these things are different in case of double positive and double negative materials. Now let us look into some of the wave propagation characteristics in a single negative and a double negative media. So for simplicity, we can consider a monochromatic plane wave with electric and magnetic field amplitudes which are given by these vectors. Okay, so let's consider ER as E0 exponential minus j k dot r, and HR is basically H0 exponential minus j k dot r. Okay, so what is k here? K is basically the wave vector. So Maxwell's equation then require these conditions to be satisfied, which is k cross h equals minus omega epsilon E naught, and k cross E naught is basically omega mu H naught. So the knowledge of E can give you H, the knowledge of H can give you E, and that is how they are basically interconnected, right? And from the information of the wave vector, you can also know about the associated wave number k, okay, which is basically the amplitude of this vector, that can be related to omega square root of epsilon mu. And another parameter, which is the impedance, that is basically the ratio of the magnitudes of the electric field amplitude and the magnetic field amplitude, and you can calculate it as eta, which is given as omega mu over k, or simply you can write square root of mu over epsilon. So eta can be directly written as square root of mu over epsilon. So this is the formula, and these are the important characteristics of the wave propagation through any medium. Now the wave number that we have seen is generally complex, right, and we can always break it into two parts. You can write it as k equals beta minus j gamma. So here beta and gamma both are real, and we can equate beta minus j gamma to the value of k we have seen in the previous slide, that is omega square root of epsilon mu, and from that you can determine that beta is basically this one, and in this case it is a lossless or medium, so you can take gamma equals 0. So because there is no imaginary part on the right hand side. So what is beta again? The beta is basically telling you that this is the propagation constant. So beta can be written as omega by c, okay, and determines both the wave velocity c. So c is basically c naught over n, okay, where n is the refractive index, and gamma that we have discussed, gamma is basically the field attenuation constant. In this case the gamma is 0. Okay. Now we can consider the implications of these equations for media in which epsilon and mu are real, and they can be either or both negative. So let us investigate these cases. So the first simple case that comes to our mind is a double positive medium. So here both epsilon and mu are positive, so you can simply write the E and the H vectors, and wave propagation, as I told you, that the wave vector can be determined from the right hand rule, Okay, so they actually form a right-handed set. E, H and K, they form a right-handed set, and the wave front will travel in the same direction of the power flow. Okay, that is the Poynting vector. So S and K are in the same direction. So when you consider the double positive medium, as we understood that epsilon and mu both are positive, so that your K and eta are also real, and that gives you very simple case where gamma, the attenuation constant, is basically 0. It means the amplitude of the wave will remain same as it propagates through this particular medium. Beta is a propagation constant that can be given as n times k naught. K naught is the propagation constant in vacuum. N is the refractive index of this medium, that is basically the square root epsilon r mu r. So epsilon over epsilon naught is basically epsilon r. Mu over mu naught is basically mu r. Okay, so from this you can find out. These are very general and known formula, and you can also write that eta is basically square root of epsilon by mu by epsilon. Okay, so this is basically the impedance. Okay, so support this kind of medium, they support TEM waves. So TEM means, you know, the transverse electromagnetic waves. So in this case both electric and magnetic fields are perpendicular to the direction of propagation. That means your E, H and K are mutually orthogonal, and they will form a right-handed system, which you have discussed already. Okay. Now in this medium, the last thing that remains is in the what is the direction of the energy flow. So that you can determine from the Poynting vector S, and S is calculated as half E naught cross with H naught conjugate. Okay, so this is how you can compute what is the direction of energy flow or power flow per unit area. Okay, so you can see that because E and H, they are forming a right hand system, so you can actually see that S will also propagate in the same direction because both are positive in this case. Okay, and they point in the same direction as the wave vector K, and the intensity of the wave, that is basically the power flow per unit area, can be given as I, which is real part of S, and that can be given as modulus E naught square over 2 eta. So that is how the intensity can be found out. Okay, so intensity, once again, what is intensity? It will be the power flow per unit area. Okay, and power is nothing but energy per unit area, energy per unit time. Okay, so here in power you get the time dependence, and in intensity you are getting the area dependence as well. Okay, and this diagram we have already discussed. So this is how you got your Poynting vector and wave vector both going in the same direction. Now when you move to a single negative medium, few things change. Now depending on whether your permittivity or permeability, which one is negative, okay, you can have K and eta both as imaginary. Okay, so you can calculate gamma, which is now omega square root of modulus of epsilon times modulus of mu. Okay, and when you compare it with the wave vector, you will see that the real part is not there, so beta becomes 0. Okay, so immediately you can conclude that this kind of medium, they do not support wave propagation because the propagation constant is 0. Okay, and there is a gamma is basically the attenuation factor. So this tells you the rate at which the wave will decay when the wave will enter this kind of a medium, and this is the impedance of this particular medium, that is given as j square root of modulus mu over modulus epsilon. Now these parameters correspond to an exponentially decaying field that behaves as exponential minus gamma z. So z is the propagation direction, and as I told you, gamma is basically the attenuation constant. Okay, and this we have already discussed that because beta is 0, no propagating waves are supported in this medium, and you can also find out the depth at which the wave will, the amplitude of the wave, or you can say the intensity of the wave is attenuated by a factor of 1 by E, and that happens at a depth of dp. So, that can be correlated to 1 by 2 gamma, and when you put the other important factors in this equation that determines gamma, you can write this as lambda naught over 4 pi square root of epsilon over epsilon naught, the thing in modulus, and then you have multiplied by mu over mu naught, okay, modulus of that. So, this actually gives you the penetration depth or the skin depth of that particular material, and this is what we know about the skin depth of metal and other things. Okay, the same concept is there in the microwave domain as well. Okay, and the imaginary impedance that we see here, that indicates that there is a pi by 2 phase shift, that J factor is there. So, that gives you a pi by 2 phase shift between the electric and magnetic fields. And when you calculate the Poynting vector is basically half of E cross H, E naught cross H naught conjugate, and this also comes out to be imaginary. And in that case, if you try to calculate what is the intensity of this particular wave, you will see that the intensity will be real part of S, and that is 0. That means no power is basically transported through this medium, and that makes sense because the propagation constant is also 0. So, from that, when you move on to the next category, which is basically double negative medium. So, you know that your permittivity and permeability, epsilon and mu, both are negative. So, when you do that, you can actually see that what happens to K. The K is dependent on omega square root of modulus epsilon times modulus mu. If both are negative, but there are modulus, so actually K is real. So, you are actually having a K that is real, that means beta will be n k naught, and you are actually able to have wave propagation. Here gamma is 0, the attenuation constant is 0, okay, and then n is given as minus square root of modulus E over epsilon naught times modulus mu over epsilon naught, and you will see that is how you are actually getting a negative refractive index. Okay, and the impedance of this media is given by square root of modulus mu over modulus epsilon. Fine. So, these are the important things. So, always remember that in this kind of media, wave propagation is possible. You can get negative refractive index, you can actually have no attenuation when the wave propagates, okay, and the choice of sign for the square roots is established by, so these are basically the sign, right, of the square roots. Whenever you take square root is plus minus, right, but then when both are negative, you can actually take the negative one. Okay, so these are actually chosen in a process by examining the direction of the vectors E naught, H naught and K, and they may be directly determined from the Maxwell's equation as well to satisfy the Maxwell's equation. Okay. So, if you see the equations for electric field and magnetic field, how they are interrelated in a double negative medium, this is how the equations are now changed. Okay, so, you have K cross H naught, which is basically omega modulus of epsilon E naught, okay, and K cross E naught is minus omega modulus of mu H naught. Okay. So, just in the case we have seen for DPS medium, like double positive medium, that E naught, H naught and K are mutually orthogonal. Okay. So, here also you can try to establish this fact that they are also orthogonal. Okay. Just that there is some kind of sign that is reversed. In the previous case the negative sign was here, now the sign has come here, right, and that is where you have to exchange the roles of the electric and magnetic fields. Okay, and that is how you can think of how to draw the E, H and K vectors in the case of a left-handed medium, right. So it is apparent that E naught, H naught and K in a double positive media, they form a right-handed set of vectors, right. So when you actually switch E and H field, that is what we see here, right, that because the negative sign was previously here, now it is here. So you can actually exchange the roles of the electric and magnetic field, and if you do that, this is how you will get, okay. So in the double positive medium, E was here, H was here, but now you have switched their roles, okay, and you actually got a left-handed system. Why it is the left-handed system? Because E cross H, okay, you have to, you take your fingers in the direction of E and roll it towards H, you will see that your thumb is directing towards the K vector, and this you can only do using your left hand, okay. So this is a left-handed system. Now when you compute eta, you will see that the impedance eta is positive, okay. However, the wave number K is taken to be negative, and therefore the refractive index also comes out to be negative. So this kind of double negative materials are called DNG materials, and they are also called NIM materials, negative index materials. So okay, before we go there, yeah, here you can also see that the wave propagation happens in this direction, but when you take E cross H, okay, that happens in this direction, right. So the wave propagation and the Poynting vector, they are in opposite direction. So the energy flow will happen opposite direction of the wave propagation. So if you put these two figures are actually showing the same thing, just that if you put it in the same manner the way you kept it for the double positive system. So here you will see that everything else remains same other than the wave propagation direction, which was on the towards right in the double positive system. Here it changes to left. That's the only difference. Now why this has happened, we have discussed that the equation has got a negative sign, and because the permittivities here are negative. So if you absorb the negative sign into the magnetic field only, okay. So first we will look into the Maxwell's equation here to start with, that you have a material which has got mu to be negative. So mu is basically minus mu, and you have got a negative epsilon as well. So epsilon is basically a minus epsilon. So you have negative signs on both cases, okay, and you are trying to push this negative sign to the H vector, okay, H field. So when you do that, you actually can get this kind of a system, okay. So this system is basically a left-handed system. So only thing that you have done here is that negative sign of permittivity and permeability, you are pushing it to the H vector, so that the H vector will flip its sign. But then when you put it in the handedness, so K is perpendicular to E, and that should be now perpendicular to minus H. In a double positive system, this was basically H, here it is a minus H, okay, and that's all. So this gives you a left-handed system. If you consider the K vector in more details and try to split it in the real part and the imaginary part, okay, you can actually get this kind of a diagram, where you can also consider your epsilon to be complex, mu to be complex. So this is the overall situation. So epsilon complex will have a real part that we'll call as epsilon prime. It will have an imaginary part, that is epsilon double prime, okay. Similarly mu will also, mu is a complex number, so mu can also have real and imaginary, that is mu prime and mu double prime. And you can see here that these are the region. So this is the boundary that tells us, okay, where that this portion will be right hand material. So you have epsilon prime mu double prime plus epsilon double prime mu prime less than 0, okay. And when this is satisfied here, it's a right hand material. Below this, in the different color that you see, this is basically left hand material, right? Okay. And another important factor that you can see from this graph is that this is the portion where you can actually have so this is the region where you can have propagating waves, okay, these two cases. So you can actually find out how you land up here by the choice of materials, okay. And in these two cases you have propagating waves. If you do not satisfy, so here what will be the line here? So this particular line is basically telling you that on this side it is epsilon prime mu double prime plus epsilon double prime mu prime has to be greater than 0, okay. So it's a positive one, and this also tells you that you have this quantity should be negative, okay. And if this two satisfies, you actually get a evanescent wave here, okay. And that is where the waves are like evanescent waves cannot propagate, they will be simply dying, okay. You can get propagating waves here, you can also get propagating waves here, okay, and you can get evanescent wave in this particular region again, okay. So that is how you can actually read this particular graph, that depending on, because in all other cases we have not considered epsilon and mu to be complex, but if you have epsilon mu to be complex, you can actually calculate this and see where your material is landing, and you can from this chart you can find out whether it will be a evanescent wave, it will be a propagating wave. If it is a propagating wave, if it is an evanescent wave in a normal medium, it will decay, right. Normal medium in the sense, if it is a DPS medium or if it is a single negative medium, it will decay. But if it is an evanescent wave in a negative index material or double negative material, the evanescent waves will grow, okay. Instead of decaying, they will grow. So all this information you can actually obtain from this particular graph, which is a plot between the real part and the imaginary parts of the wave number. So if you remember from the previous lecture, that how do we realize this kind of negative handed or left handed metamaterials? The first thing is that we can actually go with wire based arrays, and this can give us negative permittivity over a certain frequency range, and you can also decide by changing the dimension and the array periodicity, that what will be the plasma frequency below which the material will behave like a metal. We have also seen this case where we have designed an array of split ring resonators, and that could give us negative negative permeability. But always remember, these are kind of complex values, so we are basically there is a typo here, this is basically a mu r, okay. And we are looking into the real part of the permeability, okay. In the previous case also we have actually seen into this region, the shaded region, which is basically showing the real part of the permittivity, okay. So here also we are bothered about the real part of the permeability, which is negative for a very small for a very small frequency range. Now if you want to make a metamaterial which has got both negative permittivity and negative permeability in the same frequency window, what you have to do? You have to take this one and also this one, both are having negative values at the same wavelength range, okay, and you can add them up together. So here you can see, so it's starting from 1 to say 1.5, here also 1 to 1.5, these are normalist frequencies, so they can be matched, and you can see that this and this, if they are combined, they will probably give you what you are looking at. you can make a combined array of this, and you will be able to get negative permittivity as well as negative permeability over a certain frequency window, and that will give you negative refractive index. Now, this negative refractive index also gives rise to some exotic effects, something like negative or inverse Doppler shift. Now, what is Doppler shift? I believe all of you are aware of Doppler shift. It is basically the effect in light or sound. Okay, you can have Doppler shift in sound as well. So, if you consider Doppler shift in light here, it is observed as a shift to shorter or bluer wavelengths when the light originates from objects which is moving towards us at a very great speed. Okay. In terms of frequency, you can say the frequency increases or the wavelength is decreasing, and that is why it is shifting towards shorter bluer wavelengths. Okay. The opposite effect will happen when the source moves away from us, the frequency decreases. That means the shift will be towards longer or red wavelength. Okay. So, that is what the blue shift is seen when the object moves towards us, and red shift is seen when the object moves away from us, and this is how a normal Doppler shift works in a right-handed material. Now, if you want to observe inverse Doppler shift, it means there the particles that make up a wave need to move in one direction, but the intensity variation of the light's peak and valleys in the wave, that should shape the other. Okay. So, that should move in the other direction. So, that can only happen in some kind of material which is not naturally found. Okay. So, usually there are natural materials in which intensity variation moves slower than the particles in it, but materials in which they will move in the opposite direction, they do not exist in nature. Okay. It means you can only realize them using some artificial structures, and that is where some unique things are seen using this kind of left-handed materials. Okay. So, here is one example. So, this is one beam directed at the detector via a medium which has got a positive refractive index, and in this case it is again identical beam which is passing through a photonic crystal with negative refractive index, and it can actually show us the reverse or inverse Doppler effect. Now, how it works, let me explain. Here the photonic crystal was mounted on a platform that moved toward the detector at a constant speed, and the Doppler shifts were measured from the interference patterns of the beams at the detectors, and this could give us a clear verification of the inverse Doppler effect at optical wavelength. So, here when the source was moving towards the detector, you were seeing red shift instead of a normal blue shift. So, that is what you were able to see. So, here you will see red shift, and when it is going away you are supposed to see blue shift, but you are seeing you are supposed to see red shift, but you are seeing blue shift. Okay. So, I believe this diagram is clear. So, when the source is moving towards the detector with some velocity, okay, the frequency should increase or the wavelength should get shorter, so it should become blue. You can see the squeezing of the pulse here, that means the frequency has increased or the wavelength has decreased, and when the source is moving away from the detector in this direction, if it moves, the frequency reduces, it means the wavelength increases. Okay. Whereas it happens completely opposite in case of a negative index material or left-handed material. Now, left-handed materials also produce negative refraction. Now, refraction is already known to all of us since school days. It is a very interesting phenomena. If you look into this particular image, this is what we have seen in our school days many times. Also, naturally, if you stick a pipe in a juice glass, you will be able to straw you put, you will see this kind of a effect, right. So there is a bending starting from the interface, and this particular diagram actually indicates or compares the case where both the materials are positive materials, double positive materials, but in this case, case B, here one material is basically a negative refractive index material. So when you are taking that, what happens in the normal case, you see the arrow, okay, is showing the direction of wave vector, and no, the broken line with arrows, this one, the broken line with arrows show the direction of the wave vector, that will show you the k vector, and the solid lines with arrows indicate the direction of energy flow. Okay, so here you can see here the energy flow is happening this way, but the wave vector will move in the opposite direction. In this case, the energy flow also happens this way, but and the wave vector is also, the wave is also moving in the same direction, but here the wave will be seen moving in the backward direction. So when you actually produce a image of the same straw in the glass, but this time it's not water, instead of water has got refractive index of what, 1.3. so here we are considering negative index water, that means n is minus 1.3, and in that case this is how the banding will take place. So it will band on the same side of the normal, and it will look like this. So let us look into an in-depth analysis of the negative refraction. So first of all, that we have studied in our school days, that the refraction of light at the boundary between two ordinary DPS media, they obey the Snell's law. So Snell's law, as you know, it can be written as n1 sin theta 1 equals n2 sin theta 2, and in this case, this particular equation is coming from matching the components of the wave vectors k1 and k2 along the direction of the boundary. Now if one of this media, say medium 2 is replaced by a double negative medium which has got a negative refractive index of n2, in that case the equation looks like this. So you will have n1 sin theta 1 equals minus modulus of n2 sin theta 2. Now this reveals that the angle of refraction theta 2 in the case of a double negative medium, that angle should be negative, and the refracted waves and the incident waves, they will lie on the same side of the normal to the boundary, and this outcome can also be understood as it is arising from matching the components of the wave vectors k1 and k2 along the direction of the boundary. So let us look into one figure that shows that. So it is understood and clear that the optics of planar boundaries and lenses, they get significantly altered when a DPS medium is basically replaced by a DNG medium, right. So if you, for example, if you take a convex lens which is made of DNG material, that will behave like a concave lens made of DPS material, and vice versa. And if you look pictorially, what happens, the planar boundary, okay, between positive and negative materials, they actually focus, they possess focusing power. So let us look into this figure in little bit more details. So here we are considering two positive refractive index materials. So n1 n2 both are positive. So n1 is shown in a lighter shade, so this is basically a lower refractive index than n2, and this is the direction with which k1 the wave is incidenting, okay. This is theta 1, okay. So you can find out this is the cos theta component and this is the sin theta component, okay, and this is the refracted ray, this is angle theta 2. So you can also see that this is the sin theta component. So this is how you are basically matching the components of the wave vector along the boundary, and that gives you that Snell's law equation, okay. So here one important thing to mark is that though the direction slightly bends, but the propagation of wave k1 happens in this direction and k2 slightly bends, but it still moves in the similar direction. Now if you replace this medium, this N2 medium with a negative index medium, and say you are having N2 same as minus N1, in that case what can be seen that theta 2 will be same as minus theta 1. So the refracted ray will also lie on the same side of the normal. It will not go to the other side, it will lie on the same side. Energy flow will happen along this direction, but the wave propagation in this media will happen in the backward direction. So here you can see K1 is falling on the interface, but you will see K2, it looks like as if it is propagating backward, but the energy is flowing in the opposite direction. So this is how negative refraction takes place. Okay. So the planar boundary that acts on the optical ray in the same way as does a convex spherical boundary between two DPS medium. So here using a planar boundary between a DPS and DNG medium, you are basically creating a lens which is otherwise created by a convex spherical boundary if you consider only DPS medium. So this kind of metamaterials will encourage you to have planar optical components, and that saves a lot of space when you try to design compact optical or integrated photonic systems. Moreover, for DPS and DNG medium with permittivities and permeabilities having the same magnitudes, so if you consider epsilon 2 to have same as epsilon 1 but negative, so epsilon 2 is minus epsilon 1 and mu 2 you can consider as minus mu 1. In those cases, the impedance eta 1 will be square root of mu 1 epsilon 1 and eta 2 will be square root of mu 2 epsilon 2, and they both will be equal and the same sign. So in that case what happens, no reflection will occur at the boundary, okay, at any inclination regardless of the polarization. That means you are able to then pass all the light ray that is falling on that kind of interface to the other side of the interface, and you can get rid of all the reflection losses. So that is also a big advantage of this kind of materials. So with that we'll stop here, and in the next lecture we'll go into more details of the examples using negative index materials such as perfect lens. Thank you.